All right, welcome back, everyone. Just a few final people trickling in. So today it's my pleasure to introduce our speaker, Vahid Zare. Vahid just started his his PhD with Dr. Salvatore Federico in 2022. Vahid is originally from Iran, where he completed his bachelor's degree in mechanical engineering at the Islamic Azad University, and then a master's degree in mechanical university from Yazd University, Yazd University, where he studied modeling and analysis of the wire tool vibration and WEDM. Now he's moved on to doing more mathematical modeling, where he's specifically interested in using continuum mechanics to study the structure-function relationships of skeletal muscle. And without further ado, I'll turn it over to him for his talk, where he'll be discussing force enhancement as a remodeling phenomenon, a continuum model to enrich the cross-bridge theory.
Okay, thank you, Michael, for the introduction. Again, my name is Vahid, and I am currently working with Dr. Federico in the mechanical engineering department. So my topic is about the force enhancement as a remodeling phenomena. So what basically we are going to try to do is to enrich the cross-bridge theory by a continuum model. So I am speaking of a model. What do we need when we are talking about a model? So the fundamental question is that why do we need a holistic model for the muscle and muscle contraction? First one is to simulate and predict force production in muscle. The second one is to reproduce the experimentally observed history-dependent behavior of the muscle, and to reproduce healthy and pathological behaviors such as myopathy and sarcopenia. And lastly, basically one of the facts that we are going to need to the model is to serve as a basis for bio-inspired material for manufacturing, like artificial muscle to use in robotic arms and other things that they need these days. So now that we found that why do we need a mechanical model of the muscle, we need to explore a little bit about the work that has been done so far. The first known mechanical model or the model of the muscle is related to Hill. He introduced the force-velocity relationship of the contraction of the muscle in a linear equation. And the second predominant one was related to Huxley, that he introduced the cross-bridge theory. I will get into that later. After Huxley, there have been like other attempts to again model the muscle. For example, Epstein and Herzog, they tried to model the muscle geometrically. Of course, the skeletal muscle, because the geometrical shape of other type of muscle are different. And they actually, Herzog attempted to model the muscle behavior, the contraction of the muscle, due to the role of the elasticity of the titan as well. So another thing that has been been studied, but there is no actual mechanical model for it, is the force enhancement in the eccentric contraction of the muscle. So the muscle fiber will actually produce more force when it is stretched in the activation like a state. This phenomenon has not been studied in the mechanical behavior yet. So hopefully we will have a robust and reliable model based on these things later. So the fundamental properties of the muscle contraction that has been studied was first the force velocity, as I mentioned earlier, that is related to Hill. So basically, muscle will produce more force when the muscle fiber is contracting in a lower velocity, whereas in like higher velocities, the muscle is incapable of producing that much force. And another relationship that has been introduced is related to the force length relationship of the muscle fiber. So basically, we have this region that is the optimal part of the isometric contraction of the muscle, that the muscle will produce its highest force. The very second one that I was talking about is based on the cross-bridge theory that was introduced by Huxley in 1957. So basically, cross-bridge works in a manner that we pull the actin filament backwards with the myosin head. So these myosin head, they are already energetic. So imagine a spring that you are stretching. It has energy within, and they are ready to take the action and pull the actin backward. But there is a regulatory protein named tropomyosin that will inhibit this action. So this tropomyosin that I talked about is actually kind of like this. But in the following slide, I will get to that. Has been neglected so far in modeling. So the other attempt that I was talking about is related to the model by Epstein and Herzog. So they tried to model the mechanical behavior of the muscle in the manner of its geometrical shape. So, for example, for different pronation of the muscle will produce is capable of like producing a different kind of forces, different magnitude of forces. The other model that was introduced by Schapacher is the active stress model, considering the contribution of Titan in force production of eccentric contraction. So basically, what she had done in her research was to contribute the Titan to the force production of the muscle fiber, so that as you can see here in this graph, the Titan will attach in the eccentric contraction. The Titan will attach the actin, and it will alter its stiffness of. If you imagine again the Titan as a spring, the stiffness of the Titan will alter, and this will result to the alteration of the force production of the muscle. So now that we have some idea that what has been done so far, we need to know the downside of some of these models. So, for example, they are incapable of explaining some nonlinearities of the inherent of the muscle. So, for example, they are incapable of explaining the some phenomena like response to jump. They are incapable of predicting some aspects of force production in muscle, such as the ascending link of the force-length relationship and the history-dependent properties of the muscle, like the force enhancement and force suppression. And also, they are neglecting the fact that the elements of the muscle fiber, they are elastic. But in their model, they are neglecting that, and they are like taking it as a rigid bodies, and they are not accounting for the molecular level of interaction. So the cross-bridge theory again, as I mentioned, they took the elements of the muscle as rigid bodies, but just those like cross bridges or those myosins as like moving parts. In fact, it is not true. Actin and myosin are known to have elastic behavior. So this actin literature that I was reviewing, that actin differs its stiffness, its elasticity, depending on whether tropomyosin is present or not, and the contribution of the regulatory tropomyosin filament to the contractile mechanism. This last one is actually my interest, and will like have some impact on like modeling the mechanical model. So the purpose here is to develop a mechanical model to expand the one that has already been there. So we need to introduce residual force enhancement, the residual force depression, role of tighten in the elastic and inelastic behavior of the muscle, and biological and molecular level information of muscle fibers that includes tropomyosin and the role of tighten. So now that we get to know the structure, the working rules of the muscle, we need to model it. So we need a mathematical tool to model our environment, our medium, and continuum mechanics is the best tool to model every continuous medium, and it will give us the basic of the thing that we need to model our medium. So it can be used, as it can be seen here, in fluid mechanics, in solid mechanics, or even in like biological tissues. So continuum mechanics is when we are modeling some medium with continuum mechanics, we need to consider three major rules. So the first one is kinematics. Kinematics deals with the change of configuration of the body. The balance equations will deal with the balance laws, including balance of energy and mass. And the last one is constitutive equations that will be our most interesting thing to deal with, because for different medium, the constitutive equations will be different. And again, we need to model our medium according to that constitutive equations. So for modeling the muscle, we need first to determine the class of material symmetry. So for example, the skeletal muscle is known to be have a transversely isotropic fiber reinforced porous behavior and material. Whereas myocardium tissue, they have orthotropic fiber reinforced material. And then when we found out that we know which type of material symmetry that we are dealing with, we need to go to the constitutive behavior. So this constitutive behavior, we actually can work it with like passive and active behavior. This is the black box that we like imagine what is happening, what is going on within the muscle. Or we can use the cross bridge one. So for the next step will be decomposing the configuration that we have for our muscle. So we need to introduce the will be chronically decomposition of the deformation that has actually two states: the current configuration and the reference configuration and the current configuration. In the manner of modeling active and elastic materials, like muscle that has also elastic behavior. We need another configuration, another imaginary configuration that we can introduce, and then we can write the decomposition of the deformation in a multiplicative decomposition of the elastic configuration and the active configurations. So for our medium, that is one-dimensional. Basically, when we want to model the muscle fiber, we are dealing with a single fiber, and this is a one-dimensional medium. So as it can be seen, like our previous slide, we have three configuration, the reference length, the rest length, and the current length. Again, we can introduce the strain in a manner of elastic and active behavior. So what we were thinking to take action actually when we were like modeling the muscle was to introduce the balance laws, and these balance laws, the first one actually deals with the general and global balance laws that will deal with the external traction and the internal stress of the medium that is general again for every medium that you are dealing with. And the second one is actually the non-standard forces that we want to introduce to again better explain the behavior and the mechanical behavior of the muscle. So this equation, this non-standard force contains different parts that the most important one is the activation parameter that we are dealing with, we want to deal with. So in the next slide, yeah. So the activation parameter will have like different. You can actually prescribe different things to that parameter. So for example, you can take the concentration of calcium, the gradient of the concentration of the calcium, and other things. So current thinking is that is tropomyosin that I was talking about earlier, is it really contributing to the force enhancement and the force production of the muscle fiber or not? Because as the mechanism of the tropomyosin is explained, it will it will expose the binding sites of actin to truss bridges so that the muscle can contract. So basically what we are thinking is that the alteration of this tropomyosin will have like some effect on the contraction mechanism. Then we can use that alteration of configuration in our activation parameter. Then we can introduce that into our non-standard balance law. And again, we can use it to again explain the force enhancement in that configuration that I explained here. Yes, that's it. One.
Right. Thank you, Vahid, for the talk. Do we have any questions people would like to start? Yes.
Okay, thanks, Vahid, for your awesome presentation. Would you please go to slide 12? So you said something, I don't remember your exact wording, but you said continuum mechanics is the best tool to deal with.
To model continuous medium. So basically every medium that we are dealing with can be modeled as a continuous like medium.
But you said that is the best tool. How do you know that that is the best tool?
It's the fundamental and in our belief that it is the best tool because again, every medium that we are dealing with is continuous. It's true that in like subatomical like fraction, they are not continuous, but those things we are not concerned about when we are modeling in like human size or like real life.
Sounds good.
Okay. I'm going to follow up on that one. You know, like on the left there, you have the beam. Why would I use continuum mechanics for when I apply force at the end of a beam? Why would I not use a beam equation, a very simple beam equation?
The beam equation, yeah, I understand. The beam equation is actually derived from continuum mechanics.
Do I have to go through continuum mechanics?
No, basically done because it has already been done by someone else. Those beam equations that you are talking about, those have already been done according to the hypothesis of the beam through, again, continuum mechanics. And this beam equation is like ready for us to use to further like simulate the behavior of.
Okay, I'm gonna take, yeah, Venus.
I think at some point you said that Hill's equation of the force velocity
Yes,
is a linear equation.
yes, it's a linear.
How come? I believe it's not.
This one that I presented, because the actual equation, it doesn't have any nonlinearity term in that, in the inherent like of the equation. But again, you are right. For this that I was presenting, this one you mean, yeah? So for this, maybe it was not actually introduced by Hill. It was like introduced later, but the actual equation doesn't have any nonlinear term in
Go back to
it. Yeah, actually, it has like some constant, but there is no nonlinear term in that equation. So it is actually a linear equation.
Perhaps.
I was wondering about the constitutive equation and what is your plan for finding different coefficients?
Actually, that's the main part of our work. So for this, we are thinking to contribute different facts into our relation. So for example, as I was discussing, the role of tropomyosin could be a fact that we can plug into our constitutive equations, so we can better understand and better explain the behavior through like tropomyosin or other elements.
So are you going to model it as an orthotropic material or?
No, because since we are dealing with the skeletal muscle, it's going to be transversely isotropic method.
And if I remember correctly, the strain diagram for a muscle is highly nonlinear. How are you considering that in your equation?
Yes, the nonlinearity is there. That's why I was talking about some of the downsides of the models that have been there. So this nonlinearity was not explained to the full. Again, I am not the one who will explain it to the full, but we should try.
And are you hoping to use finite element analysis for this, or?
First, we need a robust model. Then, for like analyzing and simulating, we should see.
Many years ago, I tried to do the same thing for vibration analysis of the muscle, and the equations are, because of the small nonlinearity, the equations become very highly nonlinear to the point that it's almost impossible to solve.
Exactly. So you were probably using the models that they are not robust enough. That's why we are proposing a new model, hopefully potentially that will be robust enough that will not produce those. When we are simulating, will not produce those nonlinearities.
But I want to follow up on that because Arash is very clever, and there's a lot of very clever people who have tried to come up with this constitutive equation of muscle. And I think one of the problems that people have always run into is that there's not really a constitutive equation because it continuously changes its activation and other things, and it's great that you want to tackle that, but it would be nice if you told us maybe a little bit more how you can overcome these difficulties that some very clever people in the past, I don't think, have really master because I'm not aware of really a constitutive equation of muscle that I can plug in and it just
You are
works.
totally right.
So it's a big statement. And so how do you conceptually try to do that to overcome what previous people have not been able to do?
So for one thing that I was focusing on this presentation and again on my work is actually defining the role of tropomyosin in the contraction mechanism. So this has been neglected, and no one ever had like a mod or an experiment with or without the role of tropomyosin in the contraction of the muscle. So this maybe we can like maybe not. Again, I'm not like saying we can, but this maybe will be the key ingredient to introduce a constitutive equation.
But I don't think what you said is quite correct because I'm thinking, for example, about work by George Zahalak, who used calcium activation, binding to troponin, that then changed the configuration of tropomyosin, and depending on if calcium, 1 or 2 calciums were bound to troponin, thereby changing the configuration of tropomyosin, that was actually incorporated in his activation model. So I could argue some people have definitely thought about that. Are you aware of Zahalak's work?
No, but the thing is that yes, you are talking about the troponin C, and this troponin C actually like regulates the tropomyosin.
Correct.
And
that has been done by,
yes,
by various people.
But again, we don't know the exact contribution of the tropomyosin itself.
In terms of?
In terms of the cross-bridge cycle. So is it like a matter that it will expose more binding sites to the cross bridges that it will result in different force production or not? Just the troponin C can regulate that tropomyosin like alone.
I mean, the current thinking is that you have calcium, it binds to troponin C, the whole tropomyosin complex is moving away from the binding site, from the possible binding site of myosin, and then the cross-bridge head of myosin can attach. So the idea is calcium is there, cross-bridge can attach, calcium is not there, cross-bridge cannot attach. So is your thinking different than that, or?
Yeah, as I was mentioning, this exposure, what we are thinking, how this exposure will happen in the contractile mechanism. So the thing that you are saying, yes, the calcium will bind on troponin C, and it will alter the configuration of the tropomyosin. But is it all the alteration that the tropomyosin can do on the tropomyosin, or is it just like a halfway or a third way of the exposure that it can do? Can it be more exposure, or can it be less exposure? Because as I was explaining, the cross bridge is already there. The myosin heads, they are energetic. You don't need to do anything to like put more force or more energy into those myosin heads. The thing is that is actually regulates these myosin head is the tropomyosin that is wrapped around actin that will regulate those cross bridges. So the thinking is that is like exposing more to these cross bridges will alter the production of force, or is it going to be the same?
How?
Yes.
Because we know that when calcium attaches to troponin C, tropomyosin moves a little bit. and then cross pitches attach and go into a strongly bound state, tropomyosin moves more. And so if you're now arguing that that additional movement is regulating force, then how would you do that? Because that has not been described.
This is actually the part that I am not so really sure about. That we need to like again review the literature a little bit more and see whether it is possible to do such a thing or not.
Such a thing meaning?
Such a thing meaning to altering the exposure of tropomyosin on the binding sites.
On the binding sites of myosin.
Of the
myosin cross bridges.
Myosin cross bridge. Yeah. So this alteration will have effect on the force production or not?
Of the cross bridges.
Yeah.
Independently of calcium. The calcium is there, but for the same amount of calcium, you might have different behavior of tropomyosin.
Maybe yes, independently of calcium.
It's not
But-
regulated by calcium like tropomyosin.
In that manner. But again, I am not so sure what it is going to be about.
Well,
That's why
can you go back to the Titan slides that you have there, the conceptual drawing? That one, yeah,
this one.
that one, yeah. So what you have there is, in the lower figure, you have the Titan attached to the spring shortened. Compared to above where you have the full spring available. So presumably that shorter spring would be stiffer, and if you stretch, you get more force. And one of the suggestions I have made in a couple of publications, but there's really no proof there, is that when you have calcium and troponin, tropomyosin move away from the attachment sites, then you get cross-bridge attachment. If you now get into the strongly bound state, then you have a further movement of tropomyosin. And I have argued, if you have that further movement, if that frees up a binding site for Titan, then that might potentially allow for the additional force. So then you get additional passive force through an active regulation of tropomyosin. So I kind of like where you're going, but I think you need to have a certain concept there. I'm suggesting my favorite one.
Exactly.
So,
Yeah, that might be another factor affecting those force production that you proposed. But again, this will be related to the binding sites.
that would mean is tropomyosin indeed, when it goes through that second movement, when the cross pitches are strongly attached, which we know it does, is that indeed freeing something up where, for example, something like Titan might be attaching, and therefore all of a sudden you get a stronger framework.
Right. Thank you for that thought.
Well, that's kind of my favorite theory, completely unproven, but I find it really beautiful and simple, So anyway.
Thank you.
Walter, I have a question about that. Wouldn't this then require, if you're saying that the moving into the strongly bound state causes further rotation of the tropomyosin, I wouldn't expect it to occur all the way along the actin then, though, right? All you should really care about is it occurs at this one specific attachment site, which seems really difficult to predict or to not predict, but to complete So is it just, it's a random effect and it just happens to work, or, are we going to suggest that there's two different tropomyosin, complexes within one actin, that there's one that, governs the behavior of the kind of distal end and one that governs the behavior of the proximal end?
Well, Venus might know more about it than I do, but there's this sense of cooperativity, and so people have argued if you just have one site is calcium only, one troponin series calcium, then you get that movement that frees up the binding site. But when you do that, since the tropomyosin complex is 7 or 8 actin globules long, it will actually affect the next binding site as well, so that neighboring binding sites are more likely to get cross-switch attachment than if the cross-switch was not bound at that particular site. So in other words, if nothing is bound, I have an equal chance of binding anywhere. But as soon as I'm binding here, then the neighboring ones, because of the tropomyosin complex that extends beyond, it goes quite a distance along the actin film, would be greater. And there seems to be some fairly strong evidence that that's happening, that there is this cooperativity, as they call it, But the Venus might, yeah.
The answer to the question is that if we consider tropomyosin as like it sends the stress in the region that is close to the cross bridges and the overlap, the stress on tropomyosin is different than the proximal region, the deadline. And so, yeah, I would like imagine different behavior of tropomyosin, whether it's at the distal or the proximal region, is the region of the deadline.
Yeah. So I guess this then goes back to the whole thing of that the utility of the continuum mechanics model is in describing the nonlinear kind of like behavior across, because if the tropomyosin is stabilized in this one region, but then not these other regions, I guess. Cool.
But if that indeed was the case, then coming back to your constitutive modeling, let's say this is correct.
Okay.
How would you incorporate that into a constitutive equation that relates stress and strain in a unique manner,
So as I was discussing in this presentation, we are dealing with a remodeling force. That actually is the key ingredient where we can introduce this constitutive equation into that remodeling force. So for the non-standard forces that we are introducing through this equation, we need the activation parameter. So through this activation parameter that is related to different elements and factors, we can introduce that into our constitutive equation.
And engineers will accept that you have a constitutive equation that continuously changes as a function of time.
Actually, no, because there is a thing.
So. They like stress equals strain, and that's it.
There is a thing that has been said that theoreticians, no one will accept their work. That's why you are right. You're actually right. Because of the hypothesis that we are making, the simplifications and things that we need to make when we are modeling. That's why it cannot always be true. It cannot always be the best model, the global model.
Do we have any questions from anyone else in the audience? Any undergrads? Want to know what continuum mechanics is? Anything? Yes.
Can I just go back one slide? I'm not a master guy, but I was one more. Is that an attachment that change or it's a constant? If you go back one more, where you show the attachment?
So this one, this is the cross.
One more.
One more.
Sorry, maybe a few more. Where you show the muscles, they have different attachment theory of the have reinforcement force there. So then you have two springs there. One spring attached to the
the Titan one.
I was wondering if the attachment point is constant or it can change.
Let me get to that slide if I remember where was it.
Yeah, the second one, attachment is set.
This is actually not my model. This is
Okay.
This is the literature that I was.
In the literature, does that point change?
At this point, I'm not sure. I cannot answer that question.
So when you ask which point, then I think
That's
that first of all, we don't know if that binding actually happens.
okay.
But the way people think about it, that on the lower spring, the gray one,
Mhm.
that has a very specific site that combines.
Oh,
But on the straight one on top there, the actin, there, the idea is that it can attach at multiple points all along the actin. So there's one point that can bind from the lower spring there, the gray one,
Mhm.
but it can attach at multiple sites. So depending on how long the muscle is and where that yellow dot is, then you can attach at different points on the actin. That's kind of like what most people think.
okay. So if we follow this theory, so it means that the stiffness of the first spring may change. Depends on the movement and the motion. Because if you model this way, it will increase the difficulty of modeling as well. And another question, so just to go back to the slide where you showed a continuum mechanics. So want to ask you, why do you think continuum mechanics is better than a
This
beam
one?
theory? Yes. So when do you think is the best one to use like a outer beam theory? When do you think is the best scenario to use and then continuum
So the
mechanics?
answer that I was saying was that this beam theory that we are using right now in our courses in our projects, they have been developed in some point, and this development has gone through continuum mechanics. That's why.
What's the bigger difference between like a theoretical model? For example, let's see outer beam. You know outer beam?
Other beams?
Outer.
Euler. Oh,
Euler
okay.
beam.
Oh, okay.
So using outer beam, you can get relationship between force, displacement, shear force.
You can, but again, that Euler theory is based on some simplifications.
Yes,
That
I agree.
it cannot be used in every scenario.
Yes.
Then we have other beam theory that we should use, or those ones that we cannot relate to. We should introduce one for ourselves.
Yes.
This
So
is the thing that I am trying to do for muscle.
yeah, so it really depends on what is your objectives, right? If you are only focused on simple relationship like force and displacement, outer beam is perfect. You don't need to use
Yeah,
that.
it is all about your objectives.
Yes, I think it's the same for your theory. So when you talk about this, I think, have you decided which tool are you going to use? Are you trying to establish a mathematical model from the scratch, or are you trying to use, for example, finite model as your foundation and you develop based on that? I think
So that's a good question, because when you are dealing with a medium, you should go through what has been done on that medium so far. So for example, beams, you have a lot of resources on the development of the mathematical model. For muscle, there has been, but can you really relate to those literature and to those development for your own? Yes, we need to use them, but at some point, are they going to be beneficial to our work? We should decide later. That's why I said that it is an ongoing project. It has not been done yet.
is a suggestion. I think perhaps you can do it when investigate what has been done in finite model to investigate muscles, because one of my friends already investigated 3D muscles in finite modeling. Then you can see where is the gap you can build upon it. Just like suggestion.
Sorry, you said finite element?
Yeah.
So finite element is actually a tool to simulate those models.
Yes, it's a tool. Yeah.
So I'm not looking for that tool in this stage. Actually, I want to introduce a new model, a new mathematical model, that those tools can better explain the behavior of the actual muscle. So these models that have already been introduced, no matter which tool, which like mathematical tool you are using, they cannot holistically predict and explain the behavior of the muscle. That's why we need a new model. Again, I'm not sure whether it is going to be from scratch or from somebody's work, but
And last question, at the end of, so what would you expect your work at the end? What would be your ideal output from your model?
so to enrich the cross-bridge model. So,
So just that curve relationship, you want to model that.
yeah, exactly. So in the labs, there are some experiments that this cross-bridge model cannot totally explain those experiments. So what do we need is to like introduce another like model or enrich that model so it can explain those behavior that the muscle is like behaving in different kind of like conditions of experiment.
So you are interested in the force velocity relationship and a force length relationship.
Everything. So
Everything
force velocity
including
and sorry.
including muscle spin. And
Because when you have a model, you can just plug different parameters out and in and see the behavior with respect to that parameter. Do you see what I mean? So I don't know how like deep you have knowledge about the mathematical, the differential equations of the governing equations of the system. So when you want to like explain some particular part of that medium, and we are not talking about muscles right now. So anything, we need to, for example, take one parameter away and like play with that parameter to see the actual effect of this parameter on the whole system. So we will like reduce the value, increase the value, things like that, and we will then predict the behavior of the medium according to this specific parameter.
then your work would be huge. And so I was wondering, at the final stage, you need something to model to validate your model. Or do you have an idea how are you going to validate
To
your model?
validate, yes, that is another stage that I haven't gone through.
No, but I wanted to ask that too. Let's assume you have your
Yeah.
constitutive equation. And I have a muscle that I can control. What do you think would be crucial experiments that I should do with the muscle that you then predict with your model? What would be your favorite experiments
So
that
first,
somebody should do?
yeah, exactly. So first thing is the history-dependent behavior of the muscle.
So you do a force enhancement experiment, force and pressure. Yeah.
That would be my first like project.
So that would be the important second priority as well, or?
So again, the second one would be the ascending limb of the force velocity relationship. That cross-bridge cannot explain very well the ascending limb.
So what is in your model that would explain the ascending limb?
Maybe, yeah, again, I'm not sure. Maybe again, this will have something to do with the exposure of the binding sites. Maybe in like shorter lengths, the exposures are very, very little. That these cross bridges, they don't like attach to the binding sites. That could be a thing. I don't know for sure.
Well, we have an online audience. Go ahead, Salvatore. Okay, good afternoon, everyone. I am slightly out of town,
Sorry,
so I
can't
made
hear
my
you.
question remotely. I just wanted to make a little disclaimer and a comment. So the disclaimer is I don't think that continuum mechanics is the best tool to study muscle mechanics. It is my specialty. That's why we use continuum mechanics. The serious comment is that the serious comment is that yes, in fact, with this approach that Vahid has presented, the constitutive equation changes continuously because of the non-standard force in the non-standard balance equation. So yes, the constitutive equation in fact would change, would be updated at every instant. That's exactly the idea behind it. I can't hear anyone.
Sorry, Dr. Federico, can you repeat your sentence because we didn't have your voice
Okay.
all the way.
Okay, from the beginning or but from the end, from the middle, from I don't know.
From some point that we can get actually what you said.
Okay,
Because
good. So I'll try that again. I'll try that again. So disclaimer was I don't think that continuum mechanics is the best tool to study muscle mechanics. Is a tool to study muscle mechanics, and it happens to be my specialty. That's why I use that. Seriously, the constitutive equation would in fact be updated continuously, and that would be done by the external non-standard force, that activation generalized force that Vahid showed in the presentation. So the idea is exactly that there is a basic constitutive equation that then changes depending on activation. And that is at the basis of these class of models that are called active stretch or active deformation, or more improperly, but more commonly in the literature, they're called active strain type of models. So that's that is to follow up what Walter was mentioning about whether the constitutive equation was given or was continuously changing. Yeah, thank you.
Has anyone investigated a constitutive model that always changing?
Yes, actually, any active model that is based on active stretch, what we call active stretch. In the literature, you typically find active strain. Any active model that is based on active stretch updates the constitutive equation. So the active part of the deformation influences the passive part. And so the constitutive equation is not fixed. It depends on the state of the muscle, which is more or less how muscle work, right? How muscles work.
So Salvatore, aside from muscle, what
Yes.
What structure, what elements are you talking about? Where that happens?
So this has been used for active materials in general, including the artificial or the natural active materials that are not biological. For example, the materials with electromagnetic properties like piezoelectrics and so on, but those are in small deformations, so they are relatively easier to approach. And also, this is precisely what happens in plasticity. In metal plasticity, the material is still the same material, is still an elastic material, but its internal structure has been changed, and therefore the apparent mechanical behavior is different, but the material is the same. The same thing happens in our view with muscle, because the material is the same, but it has changed the internal structure. Say there are more active myosin interactions, attachments, or there is the titin that changes conformation, and those are all internal rearrangement of the structure in this view. So those are all type of, in a word, those are cases of remodeling. Those can all be encompassed by the by the idea of remodeling. That's what happens in growth and remodeling of biological tissues as well. The internal structure is changing, but the material is the same. That's the idea.
So you are not talking about nonlinear elastic material model, right?
Oh no, I'm talking about
different one.
nonlinear materials. I'm talking exactly about nonlinear materials.
Okay.
Oh yeah, that happens for linear and nonlinear. The linearity of the constitutive equation is of secondary importance at this point, because you can think of metal plasticity and piezoelectricity. Those are small deformation effects. I agree, but growth and remodeling, they are not. In biological tissues, they are large deformation type of phenomena, right? So the mathematics is exactly the same.
One of the questions, sorry. Is there any established method since the material, like probably is changing all the time, is there any established method to measure like material properties for this kind of material?
Is the question for Vahid or for me? Sorry.
Anyone can answer this question, yeah.
No, I didn't get that that question clearly.
Okay.
Can you repeat?
Yeah, for example, if it's a nonlinear elastic material, there is a way to measure different parameters for us to reconstruct this model. However, for the material model that you just mentioned, I'm not sure if there is any established way, like how we treat nonlinear elastic material.
No, there is no. There is no like.
Then how can you get those parameters to reconstruct your
Because every
constituent?
every material, they have their own behavior. It's not something global that you can like connect to every material that you are studying, because each material is different inherently in its behavior. But I'm not sure whether I have answered your question like completely or not.
Can I interject for a moment? One example that I can bring that is in a way easier than that of muscle, but it's analogous. It's that of plasticity. So if you do a tensile test on a classical metal, now we all go to the lab once in our life and see uniaxial testing of a metal sample, right? So we pull the specimen, and at some point it starts to plasticize, and so we see that the stress and strain curve changes. It's not linear anymore, and it takes a different slope and so on. But then when we unload, the curve goes down exactly parallel to the linear part, right? To the linear region, and that's the proof that the material has remained the same. It's just that we are changing the structure as we go, and so we are changing the properties, and those are measurable. Those changes are measurable. In the case of plasticity, let me put a few couples of quotations there. It's easy. For muscle, of course, it's a lot more complicated, but this can be done by changing activation, changing concentration of calcium, changing the electrical activation. So those are measurable in a way. So I assume it's difficult to do, but it is measurable. Changing the value of certain parameters. So you try to restrict to as few parameters as possible, so that you don't, so that you know what you're measuring, and then it's possible to measure the differences. And Walter can correct me if I said something totally blasphemous.
No, I think, you're right. And in muscle, we do these very simple experiments to characterize, what the properties are at any given instant in time. We measure stiffness through very quick stretches, at different activations or at different lengths. or we measure, you know, the force length property, and it's a steady state static property. But you know, I mean, we have certain ways of kind of trying to characterize the material. Unfortunately, a lot of these, like force velocity and force enhancement, force depression, and force length relationship, they all tend to be static and steady state. And the problem then is when people try to do what you're trying to do, is that you have a functioning muscle that undergoes changes in length and changes in speed and changes of activation all at the same time. You know, what is then the material property at any given instant in time? And you know, that would be then your constitutive equation. And I mean, that would be fun to have an equation like that really then predicts pretty much any behavior that's not steady state. So I think in muscle mechanics, the excuse has always been, or the approach has always been, that we measure some steady state, static type of behavior to characterize muscle, which is good, which gives us differences between muscles, but it doesn't say so much about what happens in an actual muscle contraction when we walk or run or jump or do things. Yeah.
Okay, do we have any last questions for Vahid?
It's midnight, Salvatore, for you.
Sorry, Walter?
It's midnight for you, isn't it?
It's exactly midnight and 2 minutes.
I know, you need to go to bed.
I'm already.
The only thing that I'm going to ask Salvatore here is, so Vahid is coming up with this constitutive equation. So his PhD thesis will be 1 page long with one equation. It's like the Higgs boson, Higgs article. That's 1.5 pages and won the Nobel Prize. So the one equation and the 1 page thesis. I always wanted to have a student that submits a 1 page thesis. That changes the world.
That's exactly what I was going to say. I'm hoping that that's a thesis with 1 page and 1 equation.
But we should consider that engineers are not before Nobel Prizes.
That's true.
All right. Okay. Any final questions? No? Let's thank Vahid again.